You know, there is a certain kind of question that appears at first glance to be almost childlike in its simplicity. And yet when you sit with it, when you really press your mind against it, you begin to realize that it is not simple at all. It is, in fact, one of the most profound questions a thinking person can ask. And today, that question is this: if the universe is expanding, what is it expanding into? I want you to hold that question for a moment. Do not rush to answer it. Do not reach immediately for an analogy or a comfortable image. Just sit with the raw strangeness of it. The universe, everything that exists, every atom, every galaxy, every whisper of radiation traveling through the void is growing, it is getting larger. And your mind, quite naturally, asks, larger relative to what? Into what space is it growing? What is on the other side of everything? That instinct, that reaching for an outside, is one of the most honest things about the human mind. We are creatures of space. We have lived our entire lives inside things, inside rooms, inside cities, inside atmospheres. And whenever something grows in all our experience, it grows into something else. A fire grows into the air, a tree grows into the sky, an empire grows into neighboring territory. So when someone tells you the universe is expanding, your mind does exactly what it has been trained to do for your entire life. It looks for the territory into which this expansion is occurring. And I must tell you, that instinct, however natural, is precisely where your intuition will lead you astray. To understand why, we must go back. We must go back to what we mean by space itself. And this will require us to revisit the great revolution that Albert Einstein gave to human thought in the early 20th century. Because everything, I mean everything, about this question depends on what space actually is. Before Einstein, the universe was understood through the framework of Isaac Newton. And in Newton's picture, space was a fixed, eternal, absolute container. It was like an infinite empty box that existed before anything was put into it, and would exist regardless of whether anything was inside it. God, Newton imagined, had laid down an infinite grid, perfectly rigid, perfectly flat, stretching in all directions forever. And the universe, the stars, the planets, the matter, occupied this grid. Things moved through space. Space itself did not move, did not bend, did not breathe. It simply was. This is the picture most people carry in their minds without even realizing it. When you imagine the universe expanding, you almost certainly imagine it as a ball of stuff, growing outward, pushing into this Newtonian void, this pre-existing emptiness that was there waiting. And in that picture, the question, what is it expanding into, makes perfect sense. It is expanding into the void, the empty Newtonian space that lies beyond the edge. But Einstein destroyed that picture, completely, irreversibly, beautifully destroyed it. In 1915, Einstein published his general theory of relativity, and with it came a conception of space and time that was so radical, so different from anything before it, that even today, more than a century later, most people have not truly absorbed it. Einstein told us that space and time are not a fixed background stage upon which the universe performs. They are themselves physical. They can bend, they can curve, they can stretch. They respond to matter and energy the way a rubber sheet responds to a heavy ball placed upon it. Space is not a container. Space is a participant. And this single realization, this one shift in understanding, changes everything about how we must think of cosmic expansion. Now, let me bring in the observations, because physics is not poetry. We must always return to what the universe is actually telling us through measurement. In 1929, the American astronomer Edwin Hubble published results that shook the scientific world. By carefully measuring the light coming from distant galaxies, he discovered something extraordinary. Every galaxy beyond our own local neighborhood was moving away from us. And not only that, the farther away a galaxy was, the faster it was receding. This is known as Hubble's law, and it states a remarkably clean relationship. The recession velocity of a galaxy is proportional to its distance from us. A galaxy twice as far away is receding twice as fast. A galaxy 10 times as far away is receding 10 times as fast. The universe is not just expanding here or there in some local region. It is expanding everywhere, uniformly, at every point simultaneously. Now, your first instinct might be to say, so we are at the center. Everything is running away from us. So we must be at the special point, the origin, the center of the explosion. But this conclusion is incorrect, and understanding why it is incorrect is essential to understanding the true nature of cosmic expansion. Imagine, if you will, a loaf of raisin bread rising in the oven. The raisins are the galaxies. The dough is space itself. As the bread rises, as the dough expands, every raisin moves away from every other raisin. If you were a tiny creature sitting on any one raisin, you would see all the other raisins moving away from you. You would conclude naturally that you are at the center, but of course you are not. Every raisin has exactly the same experience. There is no center. The expansion is in the dough itself, not a motion of the raisins through the dough. The galaxies are not flying through space like fragments of an explosion. The space between them is growing. New space is being created between every pair of galaxies at every moment continuously. The galaxies themselves are, in a sense, sitting still. It is the fabric between them that is stretching. This is a point of such fundamental importance that I want to dwell on it. There is a difference, a profound physical difference, between an object moving through space and space itself expanding. When an object moves through space, it has a velocity relative to other objects. It has a direction. It can be chased. In principle, you could race after it and catch it. But when space expands, there is no motion through anything. There is no speed limit being violated. There is simply more space being created everywhere. And this is why, incidentally, galaxies at the far reaches of the observable universe appear to be receding from us faster than the speed of light. Not because they are moving through space faster than light, which relativity forbids, but because the space between us and them is growing at that rate. It is the space itself that accumulates. Now let us return to the original question with all of this in mind. What is the universe expanding into? The honest answer, the answer that modern physics gives us, is that the universe is not expanding into anything. And I want to be very precise about what I mean by that, because it sounds like I am evading the question, and I am not. When we say the universe is expanding, we mean that the metric, the mathematical description of distances between points in space, is changing over time. The distances are getting larger, but this does not require an external space for the universe to expand into, any more than the surface of a balloon requires an interior for its surface to exist. Let me use this balloon analogy, which is one of the most useful in all of cosmology, while being careful about its limitations. Imagine the surface of a balloon. Draw dots on it to represent galaxies. Now inflate the balloon. All the dots move apart from each other. From the perspective of any one dot, every other dot is receding. The farther away a dot is, the faster it recedes. This is exactly the Hubble law. Now, and here is the critical point, the dots are not moving on the surface of the balloon. The surface itself is expanding. The geometry of the surface is changing. And notice something else. The surface of the balloon has no edge. There is no boundary that the dots are approaching. There is no point that is the center of the expansion on the surface itself. The center of the expansion, if you want to call it that, is not a point in the two-dimensional world of the balloon surface. It is a point in the third dimension, the interior of the balloon, which the two-dimensional surface creatures cannot access or even observe. Now, the limitation of this analogy is this. In the balloon picture, we naturally think of the balloon as sitting inside a larger three-dimensional room. We think, yes, as the balloon expands, its surface moves through the air of the room. There is clearly an outside. And you might ask, well, is our universe like the surface of the balloon, embedded in some higher dimensional space? This is actually a legitimate mathematical question, and the answer from general relativity is subtle. Mathematically, you can always embed a curved space in a higher dimensional flat space. This is known as the Nash embedding theorem, and it tells us that a four-dimensional space-time can always be embedded in a space of 10 dimensions. So in principle, yes, there could be a higher dimensional space into which our universe is embedded. But, and this is crucial, general relativity does not require this. The curvature of space-time is what we call intrinsic. It can be defined, measured, and described entirely from within the space itself, without any reference to any external dimensions. A mathematician on the surface of a sphere can determine that the surface is curved by drawing triangles and measuring their angles. The sum will be more than 180 degrees, without ever leaving the surface or appealing to a third dimension. Einstein's great insight was precisely this. We do not need an external stage. Space-time is its own stage. It curves and expands from within. There is no requirement, no physical necessity for an external space into which it is expanding. So when someone asks what the universe is expanding into, the answer is not a place. It is not an emptiness. It is not another dimension. The question, as asked, implicitly assumes a Newtonian framework, an external container that general relativity tells us simply does not exist. The universe is self-contained. It is not expanding into anything external to itself. It is simply expanding. The distances within it are increasing. That is all that is happening. But I can already hear the dissatisfaction in your minds. You are thinking, this feels like a trick, like a word game, like we are simply refusing to answer by redefining the question. Let me try to address this more deeply. The difficulty is fundamentally one of imagination. We are three-dimensional creatures. We experience space as something we move through. Our entire cognitive apparatus for understanding space is built around the experience of being inside a space with the ability to move in different directions. And crucially, in all our experience, every bounded region of space that we have ever encountered has an outside. A room has a hallway outside, a country has other countries outside, a planet has outer space outside. Our minds extrapolate from this and insist, surely the universe, being a finite region of something, must have an outside too. But this extrapolation is not valid. The universe is not a region of some larger space. The universe is space, all of it. By definition, there is no outside, because outside is a spatial concept, and the universe is the totality of space. Consider an analogy from a lower dimension. Suppose you are a two-dimensional being living on the surface of a sphere. You live your whole life on this surface. You can move north, south, east, west. You can draw maps. You can measure distances. You can travel in any direction. And if you travel far enough in any direction, you eventually come back to where you started, because the surface of a sphere is a finite space with no boundary, no edge. You will never fall off the edge. You will never reach a wall. And there is no outside of the surface that you can access, because you are a two-dimensional creature, and the outside exists only in a dimension you cannot perceive. Now extend this thinking one dimension higher. If our universe is similarly curved, if it is, in the language of cosmology, a positively curved, finite, closed universe, then it is like the three-dimensional equivalent of a sphere's surface. It is finite but has no boundary. You could travel in any direction forever and eventually return to where you began. There is no edge and there is no outside, not because we are hiding it from you, but because outside is a concept that requires a dimension beyond what the universe possesses, a dimension that may simply not exist. Now I must be honest with you. We do not know for certain whether the universe is finite or infinite. This is one of the great open questions in cosmology. Our best measurements suggest that the universe is geometrically flat, or very nearly so. Flat, in the language of general relativity, means that the large-scale geometry of space follows the rules of ordinary Euclidean geometry. Parallel lines never meet. The angles of large triangles add up to 180 degrees. The universe has zero overall curvature. A flat universe could be infinite, extending forever in all directions. And if it is infinite, then the question of what it is expanding into becomes even stranger to contemplate. Because an infinite space that is expanding is not growing at its edges. It has no edges. It is simply the case that every pair of points within it is getting farther apart. The universe was always infinite, and it remains infinite, but it is a different kind of infinite, one in which distances are increasing. If that makes your head hurt, you are in good company. Even physicists find this difficult. The idea of an infinite universe that is nonetheless expanding is genuinely counterintuitive, but it is mathematically coherent and consistent with everything we observe. What we do know from observation is this. In 1998, two independent teams of astronomers studying the brightness of distant supernovae, which are exploding stars that serve as standard candles for measuring cosmic distances, made a discovery so unexpected that it earned them the Nobel Prize in Physics in 2011. They found that the expansion of the universe is not slowing down, as everyone had assumed gravity would cause. It is speeding up. The universe is accelerating in its expansion. This was a profound shock. Gravity, the force that holds matter together, the force that had been expected to gradually break the expansion, is clearly not the dominant factor at the larger scales. Something else is at work. Something that acts like a repulsive force, pushing space apart faster and faster with time. Physicists have named this something dark energy, and it accounts for approximately 68% of the total energy content of the universe. We do not know what it is. It is one of the deepest mysteries in all of physics. It may be an intrinsic property of the vacuum of space, a kind of energy embedded in the fabric of space-time itself, what Einstein called the cosmological constant. It may be something more dynamic, something that changes over time. We do not yet know. What we do know is that this accelerating expansion has profound implications. Because if the expansion continues to accelerate, the distant galaxies, those already at the edge of our observable universe, will recede from us ever faster. Their light will become increasingly redshifted, stretched to longer and longer wavelengths as it crosses the expanding space. Eventually, these galaxies will cross what is called the cosmic event horizon, a boundary beyond which their light can never reach us, no matter how long we wait, because space between us and them is growing faster than light can cross it. In the far future, astronomers in our galaxy, billions of years from now, will look out at the sky and see only the stars of our own local group of galaxies. Everything else will have vanished beyond the observable horizon. They will see a smaller, quieter universe, and without the observational evidence we have today, they might never know that the cosmos was once filled with billions of galaxies. This is both humbling and extraordinary. It means that the observable universe, the portion of the cosmos we can in principle see and study, is not all of the universe. It is simply that portion whose light has had time to reach us in the 13.8 billion years since the Big Bang. The full universe, the unobservable regions beyond our cosmic horizon, may be vastly, incomprehensibly larger. Some estimates, based on the theory of cosmic inflation, suggest it is at least 10 to the power of 23 times larger than what we can observe, perhaps much more, perhaps infinite. Let me speak now about the Big Bang itself, because it is impossible to discuss cosmic expansion without confronting what it implies about the beginning. If the universe is expanding now and has been expanding since its beginning, then by running the film backward in our minds, we can trace it to a moment when everything was compressed into an unimaginably dense, unimaginably hot state, a state in which all the matter and energy in the observable universe was packed into a volume smaller than a grapefruit, smaller than a proton, smaller perhaps than anything we have a physical theory to describe. This initial state and its subsequent rapid expansion is what we call the Big Bang. But I must caution you against a common misconception. The Big Bang was not an explosion in space. It was an expansion of space. There was no center of the explosion in the sense we normally mean. There was no empty void into which matter was hurled. The explosion, if we must use that word, was the expansion of the spatial fabric itself, carrying matter with it. Every point in space was the origin. Every point in space experienced the beginning. And those earliest moments of the universe were not gentle. Physicists believe that in the first tiny fraction of a second, in fact, in a period lasting perhaps only 10 to the power of negative 32 seconds, the universe underwent a period of extraordinarily rapid expansion called inflation. During inflation, the universe expanded by a factor of at least 10 to the 26 in every direction. That is a 1 followed by 26 zeros. In an unimaginably brief instant, the universe went from subatomic scales to something many orders of magnitude larger. This inflation is thought to be responsible for the large-scale uniformity of the universe, the fact that when we look in opposite directions across the sky, the cosmic microwave background radiation has the same temperature to 1 part in 100,000. Without inflation, regions of the universe that are now separated by billions of light years would never have been in contact with each other, and yet they are in perfect thermal equilibrium. Inflation explains this by pointing out that they were in contact before inflation, before the universe was blown to such enormous scales. Inflation also resolves a deep puzzle about the geometry of the universe. Why is the universe so flat? The general equations of relativity allow for many possible geometries, highly curved, positively or negatively. Yet we observe near perfect flatness. Inflation provides an answer. Just as the surface of a balloon appears flat to an ant sitting on it, any curvature in the early universe would have been stretched to invisibility by the enormous expansion of inflation. What we see is a small flat patch of what may be a much larger, possibly curved hole. And here I must bring in one more idea, one that takes us to the edge of physics as it currently stands. The theory of inflation does not merely explain why the universe is flat and uniform. In its most natural formulations, it predicts something extraordinary, that inflation, once it begins, does not stop everywhere at once. In most regions, inflation ends, the energy of the inflating vacuum converts into matter and radiation, and a Big Bang occurs, producing a universe like ours. But in other regions, inflation continues, and in those continuing regions, more pockets of inflation end, producing more universes, and this process repeats forever, producing an infinite fractal foam of universes, each one a separate Big Bang, each one potentially with different physical constants, different laws, different outcomes. This is the idea known as eternal inflation, and the landscape it produces is called the multiverse. Now, does this mean our universe is expanding into the multiverse? Is the multiverse the outside we have been searching for? The answer even here is no, because, and I find this the most philosophically satisfying aspect of the entire picture, even in the multiverse framework, each universe is causally disconnected from all the others. The inflating regions between universes expand faster than light can cross them. No signal, no particle, no information can ever pass from one universe to another. They are, in the most complete sense imaginable, separate. They do not share a common space. There is no coordinate system from which you could watch our universe expanding into the space between universes, because the space between universes is itself inflating, and no observer could ever stand in that space to witness the expansion from outside. The universe, even in the grandest cosmological picture we currently possess, remains in this fundamental sense self-contained. There is no vantage point from outside. There is no exterior. There is no frame in which you can see the universe as an object sitting in a larger space, growing into a surrounding void. This is deeply strange. I know it is deeply strange, and I think we should honor the strangeness of it rather than paper over it with false comfort. The human mind evolved to navigate a world of moderate sizes, moderate speeds, moderate timescales. It was not designed by evolution or by experience to intuitively grasp a space-time fabric that curves, stretches, creates itself as it grows. The unease you feel when confronted with these ideas is not a sign of weakness. It is a sign that you are taking them seriously. There is a beautiful sentence that the physicist Richard Feynman once offered, not about this question specifically, but about quantum mechanics, that I believe applies equally here. He said that if you think you understand it, you do not understand it. The universe is strange in ways that resist the comfortable analogies we reach for. The balloon analogy helps us. The raisin bread analogy helps us. But at a certain depth, the analogies break down, and we are left face to face with the mathematics. And the mathematics tells us something our intuitions cannot hold. That space itself is the thing that expands, that there is no outside, that the universe is all there is, and that this statement is not a limitation of our knowledge, but a statement about the structure of reality. Let me bring this together before I leave you. The universe is expanding. It has been expanding since the moment of the Big Bang, 13.8 billion years ago. This expansion is not the motion of galaxies through a pre-existing empty space. It is the stretching of the spatial fabric itself, carrying galaxies apart like raisins in rising dough. The rate of this expansion is accelerating, driven by the mysterious force we call dark energy, which we do not yet understand. The geometry of the universe, as best we can measure it, is flat, meaning it obeys Euclidean geometry on the largest scales. It may be infinite, it may be finite but unbounded, like the surface of a sphere in one higher dimension. We do not yet know. What the universe is not expanding into is an external void. There is no outside. The universe is not an object moving through space. It is space, all of it, by definition. And when it expands, it creates new space within itself. The question of what it is expanding into is a question that assumes a framework, a fixed Newtonian external container that general relativity has definitively replaced. And yet I say this with genuine feeling. The fact that the question does not have a simple answer is not a failure of physics. It is one of its greatest achievements, that we have learned to ask this question clearly enough to understand why it cannot be answered in the way we initially imagined. That is science at its finest. We have gone from Newton's infinite static box to Einstein's dynamic curved spacetime. We have gone from a universe of fixed stars to a cosmos of 2 trillion galaxies rushing apart in an accelerating expansion. We have traced the history of space and time back to a singularity, and we are learning the equations that govern not just matter and energy, but the very fabric of existence. The universe does not owe us intuitive answers. It owes us true ones. And in the best and most demanding tradition of physics, we keep asking the question, pressing our mathematics harder, building our telescopes larger, refining our measurements more precisely, until the universe reveals, in its own language, what it is actually doing. And what it is doing, my friends, is extraordinary enough.